Welcome to the Deep Dive, where we plunge into the fascinating world of information to bring you the insights you need fast. Today we're tackling something truly foundational, large language models, or LLMs. You've definitely seen them in action, right?
Yeah.
Generating text that feels remarkably human, almost like a shortcut to knowledge or that superpowered assistant we all wish for sometimes.
Oh, yeah. They're certainly redefining what's possible in artificial intelligence. It's easy to get swept up in, just how capable they seem
Totally.
without fully getting the mechanics underneath.
Exactly. And that sheer scale, it just raises so many questions about how they even work under the hood. So our mission today is to kind of crack open the foundations of LLMs 2025. We're going to explore three core ideas, really. How these, digital brains actually learn language, how we interact with them, to get what we want, and crucially, how they're designed to be, hopefully, safe and effective.
Think of it like a journey. We start at the very beginning, this initial pre-training step, where the models get this huge general knowledge about language. Then we move through the more advanced techniques like prompting, which lets you guide their behavior. Then there's the critical alignment part, making sure they act responsibly.
Yeah.
And finally, we'll take a peek into the massive engineering efforts that actually power their incredible scale and efficiency. By the end, you should have a pretty solid grasp of what truly makes LLMs tick.
Awesome. Let's jump right in then. The foundation, how LLMs actually learn language. It all kicks off with something called pre-training, you said.
That's it. That's where these foundation models are born. It involves training neural networks, specifically models called transformers, on just enormous amounts of unlabeled data.
Unlabeled, so not like pictures tagged cat or dog.
Exactly. The clever part here is self-supervision. Instead of needing humans to label every single piece of data, the models learn by creating their own sort of supervision signals directly from the data itself. They essentially teach themselves the patterns of language.
Huh. So they're not just passively soaking it up, they're actively figuring it out. Can you give us a more concrete example? How does that self-supervision actually work?
Absolutely. A prominent early example is BERT. It's what's called an encoder-based model. And BERT uses two main self-supervised tasks.
Okay.
The first is masked language modeling, or MLM. Imagine a sentence where we just, hide a few words, mask them out.
Like Mad Libs?
Sort of. BERT's job is to predict those masked words by looking at all the surrounding words, both the ones before and the ones after the mask.
Oh, okay.
So if we mask raining in, it is masked today, BERT uses it is and today to figure out the missing word. It shows it's got a pretty deep understanding of context.
That's quite sophisticated, understanding context like that. What's the second task then?
The second one is next sentence prediction, or NSP. Here, BERT learns about relationships between sentences.
How they flow together.
Exactly. It gets fed two sentences, let's call them sent A and sent B, and they're separated by these special tokens markers that tell the model, okay, sentence ends here.
Got it.
And at the very start of the whole input, there's another token, CLS, which often helps summarize the overall meaning. BERT then has to predict, does sent B logically follow sent A, or is it just some random sentence? This helps it grasp narrative coherence, conversational flow.
So BERT's great at understanding language, really digging into the meaning. But how do we get from just like comprehending text to actually generating brand new coherent stuff? What was the next big step there?
Right, that's where models like T5 really made their mark. It was a shift towards what we call encoder-decoder models. These are designed for both understanding and generation.
Okay, so they can do both sides of the coin.
Exactly. And what was really innovative about T5 is its text-to-text approach. It basically framed every single task you could think of, translation, answering questions, summarizing text, you name it, as just converting one piece of text into another piece of text.
Whoa, okay. So translating Chinese is like fundamentally the same process for the model as answering, when was Albert Einstein born? Just text in, text out.
Precisely. For the translation, the input might look like translate Chinese to English, and the output it aims for is hello. For the question, input answer. When was Albert Einstein born? And the target output is, he was born on March 14th, 1879.
That's neat. It really simplifies things, doesn't it?
It does. It unified a huge range of NLP problems under this one framework. And T5 learns this similarly to BERT, in a way, by reconstructing an original sequence from a corrupted or masked version during its training.
Okay, that text-to-text idea really seems like a breakthrough for simplifying things. So we've got encoders like BERT for deep understanding, decoders like T5 doing both. But how do we get to the really powerful generative LLMs we see everywhere today, the ones writing stories or code?
Yeah, that's the evolution towards what we call decoder-only transformers. These models are the backbone of most of the modern LLMs you interact with.
Decoder only. So they focus just on the generation part.
Pretty much. Their core mechanism is called autoregressive generation. What that means is they predict the next token, that could be a word, punctuation, part of a word in a sequence, based purely on all the tokens that came before it.
So it just predicts one word after another?
Essentially, yes.
Uh,
It sounds incredibly simple, right? Predict the next word. But when you repeat that simple task billions and billions of times, training on these absolutely colossal data sets, the models accumulate this staggering amount of linguistic knowledge.
and that's how they learn grammar, style, facts, everything.
That's how they learn the patterns. It allows them to generate text that's coherent, contextually relevant, and often surprisingly creative.
Okay, wow. So learning by predicting missing words, then next sentences, and finally just predicting the very next word over and over again,
Right.
that's the core learning process. Now let's shift gears. How do we as users actually make these things work for us? Let's talk about the art of prompting.
Right, prompting. The power of prompting is, well, it's immense because it's your main way to interact with and essentially customize these LLMs without needing to do any extra training or, complicated technical tuning.
So you don't need to be a programmer.
Not at all. This ability to steer a single huge LLM to do wildly different tasks just based on the instructions you give it, that's fundamentally reshaped how we approach NLP.
It sounds like the trick is all in how you phrase your request then. So what are some key principles for crafting a good prompt?
That's a great question. Clarity and detail are absolutely paramount. If you give a general instruction, you're going to get a general response.
Makes sense.
But if you're specific, if you give details, the LLM can really tailor its output. For instance, asking, explain climate change. Okay, we'll get a broad overview.
Yeah, probably like a Wikipedia summary.
Right. But asking, explain the causes and effects of climate change to a 10-year-old child under 500 words, focusing on weather patterns and sea levels, well, that's going to give you a much more targeted and, frankly, useful answer for that specific need.
Okay, that tracks perfectly. More guidance, better result. I've also seen people kind of assigning roles to LLMs in prompts. Does that really make a difference?
Oh, absolutely. Assigning a persona or a role, like saying you are a computer scientist with deep learning expertise, can dramatically shape the LLM's response. It adopts that perspective.
So it changes the tone and the kind of information it includes.
Exactly. It makes it more authoritative on that topic or tailored to that viewpoint. Also, using structured formats for your input helps a lot. Things like Q, question A, or even using JSON-like structures can really clarify the task and what kind of output you're expecting. Makes the LLM's job easier and the results more consistent.
Right. One thing that always kind of blows my mind is how they seem to learn from examples you give them right that's in the prompt without any formal retraining. Can you unpack in-context learning a bit?
Yeah, in-context learning, or ICL, it's considered an emergent ability of these large models. They essentially learn from demonstrations within the prompt itself.
So like learning on the fly.
Kind of. Let's say you want it to classify sentiment. You could provide examples right in the prompt. Example 1, we had a delightful dinner. I label, positive. Example 2, I'm frustrated. Label, negative. Then you ask it, what is the label for? That comment was hurtful. Label.
And it just figures it out from those two examples.
Often, yes. Without actually updating its internal weights or parameters, it sees the pattern in your examples and applies it to the new case. It effectively guides the LLM down the path you've laid out with your examples.
That's incredibly powerful. Basically teaching by example in real time.
Hmm.
But okay, for really complex problems, maybe where just one or two examples aren't enough. What are the next level strategies?
You're right. For more complex stuff, we need more sophisticated prompting techniques. And one of the most impactful is called chain of thought, or COT prompting.
Jane thought.
Yeah. It's essentially showing the LLM how to reason step by step. You allow it, or rather, guide it, to break down complex problems into intermediate logical steps.
Ah, like showing your work in math class.
Precisely. That's a perfect analogy. Take a tricky math word problem like, Tom has 12 marbles. He wins 7 more, then loses 5. How many does he have now? If you just ask that straight up, some LLMs might get it wrong.
Yeah, they sometimes struggle with multi-step things.
Right. But if you provide an example in the prompt that includes the intermediate steps, like, okay, first 12 plus 7 equals 19 marbles, then 19 5 equals 14 marbles, the LLM learns to generate those reasoning steps itself for new problems. And that often leads to much more accurate answers. That's few-shot COT using examples.
Okay, so you give it a worked example.
But here's the really interesting part. There's also zero-shot COT. Sometimes, simply adding the phrase, let's think step by step at the end of your prompt can trigger the model to produce its own reasoning steps without any examples.
Just adding that phrase. Wow.
Yeah, it's surprisingly effective. It sort of unlocks that reasoning capability.
That feels like a huge leap in getting these models to, well, reason more robustly. What else is in the toolkit for really big, sprawling problems?
Another powerful technique is problem decomposition. If you have a large, multifaceted problem, it often helps to break it down into smaller, more manageable subproblems.
Divide and conquer.
Exactly. Think about writing a big report. Instead of asking the LLM for the entire thing at once, which might be overwhelming.
You might get something rambling or off topic.
Right. Instead, you could first prompt it to generate a detailed outline. Then you tackle each section individually, asking it to elaborate on point 1, then point 2, and so on.
So you guide it through smaller, manageable pieces, making sure each part is solid before moving on.
Precisely. There's even a more advanced version called the least to most method. Here, the LLM dynamically figures out the necessary subproblems and solves them in sequence. Like, if you ask for the duration of an environmental study, it might first figure out it needs the start date, prompt for that, then figure out it needs the end date, prompt for that, and then calculate the duration.
That's very systematic. But what happens when the LLM does generate something and it's, well, not quite right? Can it fix its own mistakes?
Absolutely. That's where self-refinement comes into play. LLMs can be prompted to critique and improve their own outputs, often iteratively.
How does that work?
Imagine you ask for a translation. It gives you one. Then you can follow up with a prompt like, please refine this translation. Or maybe something more specific like, correct any grammatical errors in the previous translation. The LLM will then try to improve on its first attempt.
So it's a cycle. Predict, get feedback, refine.
Exactly. Some more advanced methods even involve a deliberate, then generate approach, where the LLM first tries to identify the types of errors in its output before it attempts to refine it.
That's getting quite sophisticated. Now, what's really fascinating is how LLMs deal with their own knowledge limits. They obviously don't know everything, especially recent events. How do they handle facts that might be out of date or just weren't in their training data?
That's a great point, and it leads us to retrieval augmented generation, or RAG, and also tool use.
So RAG and tool use. Okay.
With RAG, the LLM combines its generative power with external knowledge sources. Think databases, document repositories, or even live search engines.
So it can look things up.
Essentially, yes. If you ask it about, say, the 2028 Olympics host city, something it might not know from its training cutoff, a RAG system can first retrieve relevant, up-to-date text from an external source, like a search engine.
And then use that info to answer.
Exactly. It then uses that retrieved text to formulate its answer, ensuring it's factually accurate and current. It makes the system much more reliable and informed.
It's like giving it a library card and internet access. And tool use takes that interaction idea even further.
It does. Tool use allows LLMs to interact with external APIs or software tools, making them act almost like autonomous agents.
Like what kind of tools?
Well, for a complex math problem like calculating the volume of a swimming pool, instead of trying to do the arithmetic itself, which LLMs can sometimes mess up, it could call an external calculator tool. It might output something like tool.calculatorExpression 1042.
And the calculator does the math, sends the result back.
Precisely. Or it might invoke a web search tool to get real-time stock prices or weather information. It dramatically extends the LLM's capabilities beyond just text, allowing it to interact with the digital world in specialized functions.
Incredible, giving them external senses and tools. And you briefly mentioned soft prompts earlier. How do they fit into this whole interaction picture?
Soft prompts. They're a bit different, a more subtle way to adapt LLMs. Instead of using explicit text instructions, soft prompts are essentially learnable, non-textual vectors or embeddings that get added to the input sequence.
So not words, but like special codes.
Kind of. Think of them as learnable instructions that the model understands directly at the embedding level. They're very efficient, computationally cheaper than using long text prompts, especially for tuning the model for specific, repeated tasks without needing full-blown fine-tuning.
Interesting. A more lightweight way to guide them. Okay, so we've covered how they learn language and how we interact with them via prompting. Now let's get into a really critical area, making LLMs responsible. The challenge of alignment.
Yes, this is absolutely crucial. It's not enough for LLMs to just be accurate or generate fluent text. They must align with human values, things like being unbiased, truthful, and, importantly, harmless.
Right, like refusing to generate dangerous content.
Exactly. A responsibly aligned model should refuse instructions for, say, building weapons or generating harmful misinformation, even if it could technically articulate those things. This is really central to the whole field of AI safety.
And I imagine getting that alignment right is, well, really hard. Human values are messy, complex, often contradictory.
That's the absolute core of the challenge. Trying to pin down the entire incredibly diverse spectrum of human ethics and values into a concrete set of rules that an AI can follow is, well, it's incredibly difficult. It's like trying to write a perfect instruction manual for being good.
Yeah, what one culture or person thinks is fine, another might not.
Precisely. And these models, being global potentially, have to navigate that immense diversity. It's a huge ongoing research problem.
So how do researchers actually try to teach them these values then? What are the methods?
One key method is supervised fine-tuning, or SFT. This happens after the initial pre-training.
Okay.
Here, the pre-trained LLM is further trained, but this time on carefully curated, labeled data. This data consists of specific instructions paired with desired responses that exemplify good behavior. For instance, training data showing how a helpful, harmless chatbot should respond in various conversational scenarios, like a healthcare context.
So you're explicitly showing it. If asked this, respond like this.
Pretty much, it directly teaches the model to follow instructions and adhere to certain conversational guidelines.
But creating all that high-quality labeled data for every possible scenario must be incredibly expensive and time-consuming.
You've hit on the main challenges. Yes, acquiring truly high-quality labeled data is a major bottleneck. It's costly. Plus, the fine-tuning process itself is computationally expensive for these massive models. And there's always the risk of what's called catastrophic forgetting.
Catastrophic forgetting.
Yeah, it's where the model, during fine-tuning on specific instructions, might actually lose some of the broad knowledge or capabilities it gained during pre-training if the process isn't managed very carefully.
Okay, so SFT helps with direct instructions. But what about those fuzzier, more subtle human preferences? Things that are hard to just write down as a rule or a label.
That's where reinforcement learning from human feedback, or RLHF, comes into its own. It's specifically designed to capture those nuanced human preferences that are difficult to just label directly as right or wrong.
Okay, how does RLHF work?
The core idea is, instead of humans labeling every single output as good or bad, humans compare multiple outputs generated by the LLM for the same prompt. They simply indicate which one they prefer, like output A is better than output B.
Ah, okay. So it's based on relative preference, not absolute judgment, like
Yeah.
picking the best essay out of a batch.
Exactly. This preference data, humans saying, I like this one more than that one, is then used to train a separate model called a reward model.
A reward model.
Yeah, this reward model learns to predict which responses humans are likely to prefer. It essentially learns to assign a numerical score, a reward, to any potential LLM output, acting as a kind of proxy for human judgment.
I see. So it learns to automate the human preference part.
Right. And then the main LLM is updated using techniques from reinforcement learning. It tries to generate responses that get the highest possible score from the reward model. So it's continuously learning to behave in ways that the reward model predicts humans will find preferable, helpful, and harmless.
That sounds incredibly powerful, but also really complex. Training the LLM, training a separate reward model, coordinating them with reinforcement learning seems like a lot of moving parts.
It is complex, absolutely, which is why researchers are always looking for simpler, more efficient methods. And one exciting development is direct preference optimization, or DPO.
DPO, what's different there?
DPO is emerging as a potentially simpler alternative to the full RLHF pipeline. The key idea is that it tries to directly optimize the LLM based on the human preference data, the A is better better than B comparisons without needing to explicitly train that separate reward model first.
Ah, so it skips the middleman, the reward model.
In essence, yes, it uses a clever mathematical formulation that allows it to adjust the LLM's policy directly from the preference data, which significantly simplifies the overall training framework while still achieving effective alignment. It's a very active area of research right now.
Okay, fascinating. Simpler but still effective alignment. All right, so we've explored how LLMs learn, how we talk to them, and how we try to make them responsible. Now let's peek behind the curtain into the engine room, so to speak. The massive engineering needed for their scale, efficiency, and handling really long inputs.
Right. Training these LLMs at scale is just an immense undertaking. It demands absolutely vast computational resources and unbelievable amounts of data. We're talking billions, sometimes trillions of text tokens, and running this training often requires hundreds, even thousands of specialized GPUs working together for weeks or months.
Wow, so how on earth do you manage that? You can't just run it on one giant computer.
No way! Distributed training is absolutely essential. You have to split the massive computational load across many different devices or machines working in parallel.
How does that breakdown actually work? Are there different strategies for splitting that up?
Yeah, there are several key techniques. Think of it like organizing a huge construction project. You have data parallelism. This is like giving multiple crews the same blueprint, the model, but having each crew work on a different batch of materials, the data.
Okay, so everyone processes different data chunks simultaneously.
Exactly. Then there's model parallelism. This is needed when the blueprint itself, the model, is too huge to fit onto a single worker's machine. So you split the model itself across different devices, with each device handling just one part of the model's calculations.
Like one team handles the foundations, another does the walls.
Sort of, yeah. And then you get into even more complex techniques like tensor parallelism, which splits up the individual mathematical operations within the model, and pipeline parallelism, which creates an assembly line where different devices work on different stages of the computation for different data chunks simultaneously, overlapping the work to keep everything busy.
It sounds incredibly complex to coordinate all of that.
It is. The goal is to break down this colossal task into pieces that can be computed efficiently in parallel and then combined correctly. No single machine could possibly handle it alone.
That's amazing engineering. But here's something that's always intrigued me. Why do LLMs seem to get so much better just by making them bigger? Throwing more data and more compute at them. It feels a bit like brute force, but it clearly works.
That's a fantastic question, and it leads us to the concept of scaling laws. Researchers discovered these empirical relationships, basically, patterns they observed, showing that model performance doesn't just increase steadily with size, it often improves according to a power law.
A power law.
Meaning that performance scales as a function of model size or the amount of training data or the computational budget raised to some exponent. A relatively small increase in scale can lead to disproportionately large jumps in capability.
So it's not linear. You get more bang for your buck as you scale up.
To a degree, yes. Discovering these scaling laws, like the chinchilla scaling law, which helped find a better balance between model size and data size, fundamentally changed AI development. It showed that scale itself wasn't just about doing the same thing bigger. It actually unlocks entirely new emergent abilities like reasoning or in-context learning that smaller models just don't have.
Wow. So size enables new qualities. Is there a limit, though?
There likely is. Scaling laws also suggest an irreducible error limit, a point beyond which simply adding more data or compute won't improve performance on a given benchmark, perhaps due to noise in the data or fundamental ambiguities in language itself.
Okay, so bigger is generally better up to a point because of these nonlinear gains. But let's talk about another challenge. Handling really long sequences, like feeding an entire book or a massive code base into an LLM. Standard transformers must struggle with that, right? Their attention mechanism sounds computationally heavy.
They absolutely do struggle with that core self-attention mechanism in a standard transformer where every token looks at every other token. Its computational cost grows quadratically with the length of the sequence.
Quadratically. Ouch. So double the lengths, 4 times the compute.
Roughly, yes. It quickly becomes computationally infeasible for very long contexts, like tens of thousands or hundreds of thousands of tokens. This is a major bottleneck for applications needing long-range understanding.
So what are the solutions? How do researchers get around this quadratic bottleneck to handle huge texts?
There are several clever approaches. One area is improving the efficiency of storing past information, often called KV cache management. instead of keeping detailed representations for all previous tokens, which gets huge.
Yeah, that cache would explode.
Right. So strategies like using fixed size sliding windows, only paying attention to the most recent tokens or methods that summarize older context more efficiently, like a cumulative average, help manage this memory burden.
Okay, smarter memory management. What else?
Another crucial area is improving positional embeddings. These are the signals that tell the model where each token is in the sequence, its absolute or relative position. Standard methods don't always work well for extremely long distances.
So they need a better internal map or compass for really long documents.
Exactly. Techniques like T5 bias or alibi modify the attention calculation itself, adding learnable biases or fixed penalties based on the distance between tokens. This implicitly helps the model handle long-range dependencies without explicitly calculating attention over the entire vast distance. And then there are methods like rotary positional embeddings, or ROB, which are quite popular now. They encode the positional information by essentially rotating the token embeddings in a complex vector space. It's mathematically elegant and allows the model to better understand relative positions even in very long sequences without the attention mechanism itself needing to explicitly consider huge distances.
So lots of innovation there. Is the ultimate dream something like infinite context, where an LLM could just process a never-ending stream of information?
That's certainly the aspiration for many researchers, yes. Being able to continuously process extremely long documents or streaming data without performance degrading or costs exploding, it's still a major ongoing research challenge, though.
And I guess evaluating whether they truly understand that whole long context must be hard too.
Extremely hard. How do you reliably test if the model genuinely understood something from page 1 when answering a question about page 500? Or if it just found a relevant snippet using some kind of clever retrieval or pattern matching within its context window?
No.
Differentiating true long-range reasoning from sophisticated pattern matching is a really tricky evaluation problem.
What an incredible journey we've taken today, really. We've gone right from the foundational steps of pre-training, how these models first learn language through self-supervision,
Predicting words, understanding
all
context,
the way to the sophisticated art of prompting, which is how we unlock their potential and guide them.
and then covering that really critical work on alignment, trying to ensure these incredibly powerful systems actually reflect human values and intentions, not just raw processing power.
Right, which is so important.
And underpinning it all, these immense, complex engineering efforts to actually scale them up, make them efficient enough to handle staggering amounts of information, and process longer and longer contexts. It's clear LLMs aren't just tools anymore. They show these truly emergent abilities in understanding, generation, reasoning. They're incredibly complex systems, constantly evolving.
Indeed. And this rapid evolution, it just brings with it such a profound responsibility, doesn't it? It really reminds me of that quote from Norbert Wiener, something like, "If we use to achieve our purposes a mechanical agency with whose operation we cannot efficiently interfere, we had better be quite sure that the purpose put into the machine is the purpose which we really desire."
That's a really powerful thought to end on. As these AI systems become more and more woven into the fabric of our lives, that question aligning their purpose with our true desires, our best intentions, it stops being just a technical problem.
It becomes fundamental.
It becomes a fundamental societal challenge. It's a responsibility we all share in shaping how these powerful systems develop and how they impact our future in ways we're probably only just beginning to grasp.
Absolutely. Well, thank you for joining us on this deep dive. We really hope you, listening in, feel much better equipped now to understand the foundations of these truly remarkable and rapidly changing technologies